Hi, today I'm presenting the creation of a framework for assessing the impacts of network formulations in the operation of hydrothermal power systems. This work was done by me and my colleagues and was supported by CAPS Foundation and the FGV Energia Research and Development Project. My name is Rosemberg. I graduated from Control Engineering from PUC-Rio and General Engineering from École Centrale Marseille in France. I hold a master's in operations research from the electrical department at PUC-Rio, and this work was done as I was a researcher in the Laboratory of Applied Mathematics, Programming and Statistics and LUMPS. Currently, I'm researching at Invenia Labs. In hydrothermal power system, a very important thing for the system operator is assessing the value of water stored in the reservoirs. Naturally, for long-term planning studies, we need to use simplified optimization models, which introduces time inconsistency. That is because we are planning on a simplified model, but we have to operate on respecting the physical constraints of reality. To assess the impacts of network simplifications, we use Hydropower Models, a package developed in Julia for hydrothermal economic dispatch optimization. This package has three main dependencies: jump.jl, a layer for describing and solving mathematical optimization models; power models, which deals with creating optimum power flow problems in jump; and stdp.jl, which provides the solution method for our multi-stage stochastic problem. In hydrothermal economic dispatch problems, we want to plan the operation of hydro-dominated electric systems such as the Brazilian national grid. The objectives of our problem are the same as optimum power flow. We want to coordinate generation and energy distribution at minimum cost for multiple periods, but now also to manage our hydro reservoirs. The big uncertainties of our problem is hydrology, but you can easily extend this to demand, fuel price, and other uncertainties. This is viewed as a multi-stage stochastic problems because the system operator has to decide at every stage to use water as a cheap resource for energy or store it for future periods of drought. That way, assessing the value of water. The following set of equations describes the decision the system operator has to do at every stage for a given volume V and uncertainty realization omega. The first term of our objective function is the immediate cost of generation, and the second term is referred as the future cost function. The set of constraints we have to attain at every stage is here referred to as big X. The state-of-the-art solution method for multi-stage stochastic problems is stochastic dual dynamic programming, which approximates the future cost functions of every stage by a piecewise linear function. As we know, reality can be best approximated by the alternating current optimum power flow model, which is non-linear, non-convex, in turn not suitable for the classical stochastic dual dynamic programming algorithm, and other tractable solution methods for multi-stage stochastic problems. Network simplifications are therefore needed, so approximation and relaxations. The figure on the right, which I borrowed from Los Alamos, indicates the relationship between the feasible region of different network formulations. Inside the alternating current non-convex feasible region, and as we relax further and further, we have, for example, SDP, and relax further, we have SOC, and then network flow, and at last, the copper plate model. The problem with planning with simplified models and operating in a complicated reality is that we end up with time-consistent policies that have detrimental effect as studied in the literature. A simple example here that everyone will understand is: imagine you're planning the birthday of your daughter and you choose to do a cake of her favorite princess. But when reality comes, you see that you have underestimated the difficulty of making that cake, and you end up with something nothing alike with what you have planned. And this has, of course, detrimental effects in her birthday party. Knowing that time inconsistent policies may have detrimental effects, how can we assess the cost gap between planning and implementation? One idea is to simulate the rolling horizon process run by the ISOs, that is, at every stage, run the STDP algorithm to approximate the future cost function of the first stage and coupled to the alternating current optimum power flow to find a feasible solution that best attains this function. But this is time consuming and maybe intractable for some studies. So Brigato in 2017 proposed a fast algorithm that modified STDP to use the model of reality, in our case, the alternating current power flow equations, to find the points where we want to approximate the future cost function and then approximate this function using the simplified model. To implement this fast algorithm, we use Hydropower Models, a package for planning and simulating the operation of hydro-dominated power systems. In hydropowermodels.jl, we leverage three main dependencies. Powermodels.jl, a package that we use to parse power system data and create both our simplified optimum power flow problem and the more realistic alternating current optimum power flow problem. In Jump, a package that it's used to describe the optimization problems and solve them in different solvers. We then add the hydro constraints and variables to both of these problems, and we pass these problems to STDP.jl, a package that originally provided the STDP algorithm, but we modify a little bit to implement the fast algorithm proposed by Brigato. As a study for this presentation, we used a medium-sized hydrothermal system with 28 buses. Hydropower Models package provides some visualization tools, for example, a grid plot that you see on the left and inflows plot that you see on the right. In our study, we compared 4 different network simplifications: the network flow relaxation, the second order cone relaxation, the DC approximation, and DC with line loss approximation. All of these were compared based on the alternating current model of reality. And in this first result, we have the cost comparison between what we planned, so what we expected our cost to be, and the implementation, what our costs actually happened in reality. So here we can see that NFA, network flow approximation, and DC had significant gaps of 17% and almost 10%, while SOC and DC provided a much better simplification approximation with negligible or zero gap. A very interesting thing here is that while SOC is a relaxation, it took much longer to solve, and DCLL, DC with line loss, as an approximation, took significantly less time and gave a similar result as SOC. Here on the left, you see the average reservoir levels across scenarios for the network simplifications we analyze. You see that NFA and DC, which had the biggest cost gaps, also have unpredictable reservoir behavior. And on the right, you have the average spot price. Both DC and NFA have very significant price spikes, which are caused by the dispatch of highly priced and polluting thermal generators. So besides the misleading signals sent to the agents in the grid, you end up having unnecessary climate impact that you could have avoided if you used better simplifications such as SOC or DCLL. For more information about this study on time and consistency, you can find it on my master's thesis. And for information about hydropower models, how to install, use it, and test the package, and use it to run your own studies on hydrothermal economic dispatch, please refer to the GitHub page of the package. Thank you.